So let's go ahead and walk through the calculations that you need to be able to perform. The first step is from the data that we collected, which was the volume of standard added and the conductivity of the solution. We want to be able to find the salinity of the solution, of the unknown solution. We can get that from several numbers here. We need the x-intercept, we need the actual salt concentration, and we need the volume that we obtain from these two values rather, the sample cup and the sample cup with water. Give me a second here, and I'm writing some numbers down. Okay. So from that, so let's go ahead and write those numbers down here just so that we've got them. The concentration of our standard is 29 milligrams per milliliter. The volume is, the volume of our unknown is first obtained from 343.97 grams minus 14.62. And that's the mass of water. And we need to remember that the density of water is 1 gram per milliliter. So this will ultimately give us a unit in milliliters once we do that subtraction. The last thing that we have is the x-intercept. And the x-intercept in this case was 2.09 milliliters. And the important point for us to remember is that at the x-intercept, that is the volume of standard that has the same amount of salt as our unknown. So we want to find out how much salt is in 2.09 milliliters of standard. So we start off with 2.09 milliliters times the 29 milligrams of salt in 1 milliliter of standard. Then these numbers are going to cancel out. And once we've got that number there, I'll leave you to calculate that number. We divide that by, so this is milligrams, we divide that by the volume, 343.97 minus 14.62, and that's milliliters. This is the concentration of the unknown, and for the data that I've got right here, it should be milligrams, 0.18 milligrams per milliliter. Okay, so you're going to do that for all three trials, or all three samples. And let's take a look at the MSA template. You'll notice that the MSA template actually answers this question for you. So if you get stuck, or if you just want to say, okay, I give up, or if you want to make sure that you get the right answer, that's there for you. From the MSA template, we need that value, and we also need this value here to calculate our errors. To analyze or to compare the results from the three different trials. So let's go ahead and look at that individually. The distilled water has an x-intercept, so this is the salinity of the distilled water, and this is the percent RME. And what we want is to get a range of values where the true value of the salinity of distilled water might be, and the range of values is actually the x value, so the salinity plus the RME, from minus the RME all the way up to the positive of the RME. So let me go ahead and crunch this number and show you how we would do this. We take the value of the x-intercept, 0.0217, and we're going to multiply that by 1 plus the RME in decimal form, so 0.3288. And when we do that, we get a number that is 0.0 0.29. And then we do the same thing. 1 minus 0.3288. And we get 0.015. So we're going to do that for the other two. If you want to pause this video and check it out to make sure that you know what you're doing, that's great. Otherwise, we can carry on. I'm going to try to. There we are. Okay. This is for the tap water. We've got the salinity of the tap water and the error of the tap water. So let's go ahead and figure out our range. I'm going to use 4 decimal places for this one, just to make sure that we get a good difference. We'll avoid any round-off errors. 1 minus 0.0897. And that value is 0.17. And then same idea, 1 plus 0.0897, and that's 0.21. Great. Okay, let's do it one more time with for the filtered water. This is actually a filtered water. And we've got 0.184 as the salinity, and the error is 9.37%. Again, 0.1844, 1 plus, and that gives us a result of 0.17. And oops, I'm sorry, this was a minus sign right here, and this is a plus sign right here. And that gives us a 0.20. So we've got the ranges for the 3 values. So let's go ahead and look at all of those together. For our DI water, or distilled water, we had 0.015 to 0.029. For the tap water, we had 0.17 to 0.21. And for the filtered water, we had 0.17 to 0.20. Notice how if we were to draw these out on a number line, we have 0 here, a 0.1, and a 0.2, that the distilled water would show up somewhere around this region here. The tap water would show up from 0.17 to 0.21, so maybe somewhere around here. So that's our tap water. And our filtered water would show up somewhere around here. Notice how there is a huge gap between the distilled water and either the filtered or tap water. What that means is the DI water is different from the filtered or the tap water. However, the filtered and the tap water both overlap one another, so there is no difference between the filtered and the tap water. So the statistics show us this. Again, in a few days, we're going to learn what statistics we've actually calculated here. But for this experiment, the data that we've just go over, the math that we've just gone over, is the math that you need to know. I've done all the number crunching for you, so if you can't fully grasp it at this point, come talk to me, but these are the answers that you need to have.